So this is lecture 10, and now we're going to start talking about the solar system. We've left the Earth. We've talked about how the Earth has gone through these periods of heavy bombardment, and now we're in this period where we're occasionally being hit by some kind of space rock, but mostly that kind of business is over. Now we're going to step out and sort of get a glimpse of what the solar system is like, you know, out to sort of the Kuiper Belt, out to sort of where Pluto is. And then from that point, we'll talk about different planets and particularly moons in the solar system that might be nice places to search for life around the sun. So here is a schematic of the solar system. Now, the distances between the planets and the sun are certainly not to scale here, but the sizes of the planets are to scale. So right here you can get a sense of just how big the sun is compared to, say, Jupiter. Here's Jupiter and here's the sun. You could take 10 Jupiters and put them across the face of the sun, okay? And this is the Earth. So the Earth is sort of similarly sized. You could take 10 Earths and put them across the face of Jupiter. So 10 Earths make a Jupiter and 10 Jupiters make a sun. Saturn is the second biggest planet in the solar system. It's out here, and it is almost as big as Jupiter, but not quite as big. And then we have these other larger planets out here. We'll step through this stuff. But if you don't remember, it's worth reminding yourself, the order of the planets is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then we have this series of small dwarf planets out here, of which Pluto is the most famous. What we're going to do is we're going to give a quick overview of our solar system. We'll talk a bit about the sun and what it's made of. The so-called terrestrial planets. Terrestrial planets are basically the inner planets like the Earth. Then the Jovian planets, so these bigger ones, these big Jupiter-like planets out here. Then we'll talk a bit about the dwarf planets, which are these little bitty things. And I'll talk a bit about why they're called dwarf planets and not called regular planets. And then finally the trans-Neptunian objects. And we've already talked a bit about asteroids and comets in the previous lecture, so I'll just sort of glance over that today. And we'll sort of emphasize the point that all of the planets in our solar system, at least, tend to lie on basically exactly the same plane, and they're orbiting around the sun in the same direction. One of the things that it's interesting to appreciate about our current point in time is that we're in basically a golden age of space exploration. Now, what I mean by that is we're at a point in time where we're sending robotic missions on, piloted missions, so missions without humans on them, but we're sending these robots all out throughout the solar system. We're doing sort of amazing things. Now, it's been a long time since we've actually sent humans to other worlds like the moon. That's been that was quite a long time ago now, and there's sort of hope that we will be sending humans up over the next 10, 20, 30 years. But at this point right now, everything that's being done is basically robotic. But just to sort of remind you, everything we've done, we've put people on the moon. We've put robotic landers on the moon, Venus, Mars, Titan, and we've even landed on an asteroid. We've recently landed on a comet. So we've done all kinds of things in terms of sending robotic missions out there. We've actually physically returned rocks from the moon. So we've taken pieces of the moon, brought them back to Earth. We've taken deep direct probes of atmospheres of Venus, Mars, Jupiter, and Titan. We've thrown spacecraft by or near all the planets, and we currently have a mission that's very, very close to Pluto, that's getting sort of locking in orbit around Pluto right now. We've got all kinds of exploration of Mars in progress right now. We've got rovers driving all over Mars. And so we've really done an amazing number of things in terms to map out and understand our solar system. There's a lot more things we want to do, but in terms of mapping out our solar system, we've already done quite a bit of that kind of thing. You could think about the things that orbit the sun. I mean, you can break them up into different categories, and so people who study the solar system tend to do this, but it's worth thinking about the different types of things that are orbiting around the sun. The inner planets are called the terrestrial planets. They tend to be made of mostly rock, so they're heavy, dense things like the Earth. So Mercury, Venus, the Earth, and Mars are all very rocky planets, and they're called the terrestrial planets. They live near the sun. The Jovian planets are Jupiter and Saturn, and then these are called gas giants. They're mostly made of gas, hydrogen, and helium. And then we have the so-called ice giants, Uranus and Neptune that are out here, these are called the Jovian planets. So these outer planets, these sort of bigger planets, are called the Jovian planets, and the inner ones are called terrestrial planets. Finally, there are these things that are sort of newly classified called dwarf planets. So dwarf planets are basically little planets. So they are massive enough that they've overcome the sort of the gravity they have has overcome sort of the tensile strength of the rock or whatever that makes them up. So they're basically spheres. But they're not big enough that they've cleared out the space that they orbit in of all smaller bodies. Okay. So, for example, Pluto, Eris, Ceres, Haumea, and Makemake are the dwarf planets that we name, and most of them are sort of beyond Neptune. You can see here that Ceres is actually a little dwarf planet that lives right here in closer to the Sun, but all these other dwarf planets live out beyond Neptune. And there's probably a lot more out there that we just haven't discovered yet. In fact, there are a lot of things that are sort of candidates for dwarf planets that are known and that are out there. Finally, there are other things that aren't even big enough to be classified as dwarf planets, and these are called, generally you just call them small solar system bodies, and these are the icy Kuiper belt objects and comets we talked a bit about last time, and then those rocky asteroids that we see in the asteroid belt and other places. So there's all kinds of stuff orbiting around the Sun. Why is this going on? Well, the Sun is this crazy big massive thing, okay? In the environment of the Sun, it's by far the most powerful gravitational field around, and so little stuff is attracted to it and tends to orbit around it. And so that's why all this stuff is orbiting around the Sun. And the biggest things have been able to accrete atmospheres and other things, and those are the planets. And of course, we live on one of those. Now, again, just to remind you, terrestrials are here. The gas giants are here, Jupiter and Saturn. These are called ice giants here, and then these things here are called the dwarf planets. Now, all of the 8 planets, okay, these 8 sort of classical planets now that we talk about, all orbit in this roughly the same plane on the sky, or sort of around the Sun, okay? And they all orbit in the same direction, and that's also the same direction that the Sun rotates. So just how the Earth rotates on an axis, the Sun also rotates. The Sun spins around, and in that same general direction that the Sun is spinning around, the planets are going around the Sun, okay? Now, if you zoom in on this inner region, that's where our sort of terrestrial planets are, and then all the way up to Neptune, these are how things are orbiting around. So the inner solar system is actually a much more crowded place. Things are more tightly packed than the outer solar system where these big giant planets are. This is an edge-on view of the orbits of the planets. And this again gives you this sense of just how tightly aligned in the same plane they all are. The fact that the planets all orbit in the same plane tells you something about the initial conditions that gave rise to the solar system, okay? So generally speaking, if you've got a big cloud of stuff like gas that is attracted to something because of gravity, the gas cloud can tend to cool off. So the reason why an initial gas cloud would be puffy is the stuff that makes up that gas is hot, and if it's hot, that means it's sort of moving in random directions and moving really fast. But eventually that gas can kind of cool itself down. Little pieces of gas collide with other pieces of gas. They excite their atoms, they emit some energy and begin to cool down and slow down. And if there's any sense of coherent spin to the thing at all, what that thing will do is it will collapse into a uniform rotating plane because it's hard to lose angular momentum. So a physicist would say that any configuration, the lowest energy state you can have is a very thin plane that conserves that angular momentum. And so it's generally expected in nature that a lot of things will end up collapsing into planes. And in fact, if you look at pictures of galaxies, like our own galaxy, the Milky Way, it's basically a plane of stars, and it's the same kind of deal. It's all rotating in basically the same direction, and you have this thin plane of stars that makes up the galaxy. On an even smaller scale, on the scale of the solar system, things collapse into a single plane. And that's why we think we have this coplanar disk of where all the planets orbit. Now, the Sun, what's the deal with the Sun? So the Sun is mostly hydrogen and helium. It's 99.8% of the mass of the solar system, and it's 4.6 gigayears old. Okay, so it's this old 4.6 giga-year-old thing that's made of mostly hydrogen and helium. And it's almost all of the mass in the solar system, including that of Jupiter, is all in the sun. So the sun just dominates by mass by far. Nothing rivals the sun in terms of its mass. And that's why the sun is sort of at the, if you think of it as at the middle in all the planets orbiting around the sun, it just has the most mass. Why does the sun shine? Like the sun shines on us, right? Why does the sun shine? The reason why the sun shines is that it's hot. Things that are hot tend to shine. In fact, anything with a temperature shines. And just like if you take an iron, like a hot iron out of a coal, hot iron out of a fire, okay, it will glow. That's because it's hot. And that phenomenon is called black body radiation. Anything that has a high temperature like that will glow. And if the temperature is high enough, it will glow in the visible light that you can actually see. And that's what the sun is doing. The surface of the sun is about 6,000 degrees Kelvin, and that means it's shining in light that's basically visible, the visible wavelengths. It's no coincidence that that's exactly the wavelength of light that we see, okay? Because it only would make sense that species living around a star that's emitting most of the light, most of its light invisible, would evolve eyes that could see in the visible. Okay? You could imagine species that evolved around a star that was emitting most of its light in the infrared. You might imagine that those species would evolve so that they could see infrared light instead of visible light. Okay. I should mention then that like we are also glowing. Okay? We are also glowing as black body radiators. We are emitting light, but we are emitting light that's in the infrared, okay? And so infrared light is what we feel is heat. We're all glowing in infrared. We just can't see that infrared light with our eyes, okay? Because we are evolved to see this visible spectrum light. So when we see each other, we're seeing reflected light. We're not seeing this sort of glowing infrared light, the heat that we're emitting. Okay, why is the sun hot? What makes it hot? So it's glowing because it's hot, it's shining because it's hot, but why is it glowing? It's shining because it's hot, but why is it hot? The reason why it's hot is there is a bunch of nuclear fusion going on in the core of the sun. Basically what's going on is the sun is mostly hydrogen, but at the heart of the sun, hydrogen atoms are being fused into helium atoms. And in the process of this fusion, they emit energy. This is nuclear energy. The origin of nuclear energy has to do with E equals mc squared. Okay, it turns out that 4 hydrogen atoms weigh a little bit more, have a little bit more mass than 1 helium atom. And the tiny amount of mass that's lost in taking 4 hydrogen atoms and fusing them to form 1 helium atom goes into energy. And the mass loss is the m. You multiply it by c squared and you get some energy out. That's an extremely, extremely efficient way of creating energy, and in fact, that's what powers the sun. Nuclear fusion is what's powering the sun. It's such an efficient use of energy that the sun can be spitting out the incredible amount of energy it spits out for 4 or 5 billion years and still have enough fuel to last for another 5 billion years. Okay. So we think that the sun is going to shine for a total of about 10 billion years by hydrogen fusion. And then it's probably got another billion years or so after that. It will actually fuse helium in its core to heavier elements before it then dies. Yeah?
Can humans, can they recreate the nuclear fusion of hydrogen and helium?
Yes, so the question is, can humans recreate the fusion of hydrogen into helium and in doing so have a great energy source? We would like to do that. So one of the big goals of plasma physics today is to build a fusion reactor. Now, we do harness nuclear energy to run some power plants, right? But those kind of power plants, the nuclear power plants that you're familiar with, that does a different thing. That's called nuclear fission. So what that does is it takes big elements, like uranium, and breaks them up into smaller elements. And it turns out that elements heavier than iron, when you break them up, they release energy. When elements are smaller than iron, you fuse them together, you release energy. Okay? So what the kind of nuclear power humans use today is fission power. Now, fission is less ideal than fusion because it creates all kinds of waste products that are radioactive, that are hard to deal with, that sort of unsafe, and you have to think hard about what you do with those waste products. The fusion energy, in principle, is better because it will produce fewer radioactive waste products, okay? And the sources that you need to make fusion happen are plentiful because it's basically hydrogen. And hydrogen is easy to make. Water is H2O, so there's all kinds of hydrogen available all throughout the oceans where you can get hydrogen. So if we had a little nuclear fusion reactor, we could just harness hydrogen from the ocean, feed it into that reactor, and power everything, right? So nuclear fusion is a great goal, and if we could crack the code of nuclear fusion, if we could create little mini suns to run our civilization, that would be a big, big deal and be a very important thing. It turns out that it's hard. The way the sun does fusion, the only way you get fusion to happen is you have to have really high densities, really high temperatures to take hydrogen atoms and fuse them together. That's because hydrogen atoms, the cores of hydrogen atoms are basically protons and they repel each other. So you can't just take two cores of hydrogen atoms and lob them at each other because the protons will repel. So what you have to do is you have to create really high temperatures and pressures so they come at each other really fast, overcome what's called the Coulomb force, that electrical repulsion, and basically make them touch. And when they touch, a new force of nature called the strong force takes over. They fuse. When that fusion happens, that releases energy. Okay? We've actually made this happen in the laboratory, but today fusion reactors, you have to put more energy in than you get out. They're not great ways of producing energy, but the goal is to eventually build something that's sort of like the sun. The other thing I should say is having a contained nuclear fusion reactor is hard because what do you put the thing in? Because you have to have these incredibly high temperatures and pressures to make this fusion happen. So how do you contain it? And what people want to use is magnetic fields. The only place where we actually successfully use nuclear fusion is in bombs. So thermonuclear bombs are fusion bombs. So you can make fusion reactions happen, but you can't control them very well. And so it's easier to make a bomb than it is to make a reactor when it comes to fusion energy. Okay? But it's a great goal that plasma physicists have to basically build little mini suns and use those mini suns to power things on Earth. For now, we have a big fusion reactor in the sky called the sun, and we're trying to harness the energy it's spitting out with solar panels and stuff like that. Okay. So the sun is spitting out a crazy, crazy big amount of energy. And it's kind of hard to wrap your brain around just how much energy the sun is spitting out. But let me remind you again that all of the energy used by basically all life on Earth comes from the sun. Okay? Photosynthesis. Okay, plants get their energy from the sun. When we eat plants, we ultimately are getting the energy locked in those sugars or whatever. That stored energy ultimately comes from the sun. Any animal, therefore, that eats plants is getting energy from the sun. And so then when we eat animals, we're ultimately getting the energy from the sun. Fossil fuels are the sort of remains of old plant matter that, again, built their carbon-based fuel from solar energy. So all of this energy ultimately comes from the sun. The sun is spitting out an incredible amount of energy. Now, the way we talk about how much energy is coming out of the sun is in terms of something called luminosity. So the sun is very luminous. It has a high luminosity. Luminosity is the energy given off per unit time. So another word for that is power, because power is the use of energy per time. So the sun has a huge amount of power or luminosity. In practice, it has 4 times 10 to the 26 joules per second of energy coming out. A joule is a unit of energy, and so joules per second is a unit of power. And in fact, a joule per second is something we call a watt. Okay? So the sun is emitting 4 times 10 to the 26 watts of light energy. Compare that to a more familiar unit of watts, okay, a 100-watt light bulb. Okay? So the sun is like 10 to the 24 100-watt light bulbs booming. Okay, so it's an incredible amount of energy. But again, a watt is a useful thing to think of. If you use the term watt, the sun is just spitting out incredibly large amounts of energy. Now, The thing that's crazy about it, right, is all of the energy that the Earth has collected, right, all of the energy from the sun that has powered all life on Earth for the history of the Earth, that keeps the Earth warm, that effectively keeps us alive, that has powered all of the fossil fuels that we use today, okay, is all come from the sun, light from the sun. But if you think about it, right, this is the Earth compared to the sun. It's, 1/100th the size of the sun. And the sun is spitting its energy out in all directions. Okay? It's not like it's beaming all of its fusion energy right at the Earth so that we can use it. It's just randomly spitting it out in all directions. So the sun spitting out energy in all directions, the Earth is only subtending this tiny little bit of it. And that tiny sliver of all the energy that the sun is spitting out, right, is what has powered all life on Earth for the history of the Earth. More or less. There's little things that aren't powered by the sun, but most things are powered by the sun. So it's an incredible amount of stuff that's coming out of the sun. So just appreciate the sun, very energetic, spitting out a lot of energy. We're only capturing just a tiny sliver of it, and that tiny sliver of solar energy we collect is so important that it sort of keeps the Earth warm and does all these things for us. Are there any questions about this? If you calculate what fraction of the energy of the sun we actually receive, it's roughly 2 billionths of the sun's energy. 2 billionths of the sun's energy is being collected by the Earth. Everything else is just going away. Now, as this light comes from the sun, it spreads out. Okay? So if you have the sun here, right, imagine it's got a bunch of energy. You can think of it as sort of like a sphere of photons that are being shot out every second or so from the sun. As this sphere of photons shoots out in all directions, its intensity is spreading out. Okay, so you might have a group of photons that come out, and you wait a little while, and now that same group of photons is spread out over a big sphere. And you wait a little bit longer, that same group is now spread out over an even bigger sphere, and an even bigger sphere. So the energy per unit area being delivered by light from the sun is falling off like the distance. And in fact, it's falling off directly proportional to the area of that sphere. The area of that sphere is 4 pi r squared. But here I've just called the distance from the sun to where you are d. So now it's 4 pi d squared. Okay, that's just the area of the sun. So what's called the flux, the power per unit area, is just the luminosity of the sun divided by the surface area of that sphere, of those spheres that are getting bigger and bigger. Okay. So what that means is, if you are twice as far away, the intensity of the sunlight you feel is 4 times lower. Right? Okay? And that makes sense. It's just like if you're really close to a campfire, you're hot. If you back up from a campfire, you get colder. The heat flux from the campfire is falling off like the distance squared, just the same way, because it's also being spread out on something that's roughly like a sphere. Does that make sense? So if you calculate how much energy per unit area is being hit, is coming into the Earth, it's roughly 1,000 watts per meter squared. Okay? So what that means is, if you put a solar panel at the top of the Earth that was 1 meter square, and you were collecting its energy 100% efficiently, you would be collecting 1,000 watts of power all the time. On average, that's enough to power your house for every meter squared that's hitting the Earth. Does that make sense? Now, what if I was farther away? So what if I was, say, here's the Earth, we're at 1 AU. What if I was sort of way out here on Neptune? Would the flux be higher or lower? Raise your hand if you think it would be higher. Good. Raise your hand if you think it would be lower. Good, right? Because it spreads out. And in fact, we know exactly how much it would spread out. It would spread out like the distance squared. Right? Okay. Now, so the energy is diluted per unit area as you go out. So here's Earth, right? Earth, you're 1 AU from the sun. The Earth is nice and warm. We have liquid water. It's a great place to be. We're very happy here on Earth. Now you travel out to Eris. Okay? Eris is 100 AU from the sun. It's very, very cold there, too cold for liquid water. Okay? In fact, you're 100 times as far away. The flux of energy falls off like the distance squared. Okay? So you're 10 to the 4 times weaker flux from the sun than you are at the Earth. So now your solar panel would have to be really, really, really big to collect the same amount of energy as it would at the surface of the Earth. By the way, this is why spacecraft, when you travel out to the outer solar system, can't be solar panel. They don't have solar panels to power what they're doing because they're so far from the sun they just can't collect that much. Whereas if you're on Mars or orbiting near an inner planet, you can have solar panels to power your telescope or your robots or whatever. Okay. So I worked this out here, but basically if you have the flux, which goes like luminosity over 4 pi d squared, the flux at Eris divided by the flux of the Earth, it's just the distance to the Earth squared divided by distance to Eris squared, that's 10 to the minus 4. This got cut off, but it's 10 to the minus 4. Okay. Now, the thing about it is, you can actually work out what the temperature of a thing should be given how far away it is from the sun. Because if it's close to the sun, it's collecting a lot of energy per unit time. If it's far away from the sun, it's collecting less energy per unit time. And you can calculate exactly what's called the equilibrium temperature of that thing should be, depending on how far away you are from the sun. In the absence of a greenhouse effect atmosphere, so let's ignore that. Let's just think about the outer part of a rocky planet with no atmosphere. You can calculate exactly what the temperature of the thing should be if you know how far away it is from the sun. Okay? And I won't go into the details of how you do that, but you can imagine one could do that. And the equation is actually this. Your equilibrium temperature ought to be about 280 Kelvin divided by the square root of the distance between you and the sun. Okay? So the farther you are away, the lower your equilibrium temperature will be. Here, A is something called the albedo. Albedo is the thing that describes how reflective you are. Okay? So if you're a mirror planet that's reflecting all the energy that comes at you, you're going to be very cold because you're not absorbing any of that energy. Okay? So if you're 100% reflective, that means your albedo is 1, and you basically are your temperature is absolute 0 because you're just not collecting any energy at all. Most planets are sort of somewhere around a half, so this number comes in. It's not a very big number. Sort of order unity number here. Okay. The point is, you can figure out exactly how hot you should be if you know how far away you are from the sun. Now, of course, if you have a greenhouse effect, as we've talked about already, this would increase the temperatures beyond this point. So this is sort of a minimum temperature you would have on the surface of a planet in the absence of a warming atmosphere. So here's some examples. Okay, here's the moon. The moon has basically no atmosphere. It has a reflectivity of an albedo of 0.12. That is, it's not that reflective. It's absorbing most of its light. Its distance from the sun is again about the same as that of the Earth, 1A2, and its equilibrium temperature is about 270 degrees. That's roughly the average temperature of the moon. Okay. Now the day side and the night side of the moon turn out are drastically different temperatures. But on average, this is a pretty good temperature for the moon. Enceladus, okay, on the other hand, is about 10 AU from the sun. This is an icy moon, okay? And it has an equilibrium temperature of about 30 Kelvin. So it's a very cold thing, and that's why it's so icy. These are just some examples. These are objects that basically don't have any atmosphere, so you can apply this equation, calculate their temperatures, and then you measure their temperatures. It's pretty close to what you see. Now, let's return again to these inner planets. Okay, so here are the inner planets of the solar system, the so-called terrestrial planets. They live from something about 0.4 AU to 1.5 AU. Remember, AU is the distance between the Earth and the sun. Mercury is only about 5% of the Earth's mass. It's this little bitty thing near the sun. Venus is almost an exact clone of the Earth. Okay, Venus is very similar to the Earth, it turns out. in the sense that it's about the same mass as the Earth, just a little closer to the sun. Here's the Earth, and then Mars is a little thing. It's really small. It's actually pretty small compared to the Earth. Its gravity is a lot weaker and all that kind of stuff, right? These planets are made of mostly silicates. That is, they're made of things out of silicon and iron, and their densities are high. So they're denser than water. They have densities of order 4 grams per cc or 5 grams per cc. Water is 1 gram per cc. Okay, so these things are pretty dense. And it's just like rock and metal. So that's what they are. Now, they also have atmospheres. And we've shown this plot before in a slightly different way, but I wanted to remind you this very interesting thing about what the atmosphere content of these different objects in the solar system are and why they have the atmospheric content that they have. You may ask yourself, you know, I've talked about this before, the outer planets like Jupiter and Saturn are made of mostly hydrogen and helium gas. And in fact, that's kind of naively what you would expect, because most of the stuff of the universe is hydrogen and helium gas. The sun is mostly hydrogen and helium, right? So almost everything in the universe is mostly hydrogen and helium. Why is the Earth and its atmosphere not made of hydrogen and helium? Okay. If our atmosphere was hydrogen and helium, that would be kind of bad for life. Okay? If you have just a hydrogen atmosphere, that is not something that's conducive to life like ours. Okay? That's not going to work so well. So why isn't it mostly hydrogen and helium? And if you recall, it's because hydrogen and helium float. Right? If I have a helium balloon and I let it go, it floats. Why does it float? It floats because the velocity of helium molecules at the temperature of the Earth is higher than the escape velocity of the Earth. And so they just fly off the Earth. Okay, if you release some helium, it does not stay on the Earth. It leaves. Okay? So you can, in fact, do these kind of comparisons for all different kinds of molecules. What's plotted here is the escape speed of different planets. Okay? So to escape the Earth, you have to be moving faster than about 11 kilometers a second. Mars is less massive than the Earth, so to escape Mars, you have to be moving faster than about 5 kilometers a second. Jupiter is much more massive than the Earth. In order to escape Jupiter, you have to be moving 70 kilometers a second. So the more massive your planet is, the higher your escape speed. So that's on the y-axis. The x-axis is the temperature of those planets. Okay? So the Earth here has a temperature right around here, sort of 2-something, 300 K. Jupiter is colder. Pluto out here is very cold, so it's down here. And so the position of the planets are just their temperatures on this axis and their escape speeds on this axis. The lines show the speeds of molecules, different kinds of molecules at those temperatures. Okay? So for example, if you have a light molecule, they tend to be moving very fast at a given temperature. So at 1,000 degrees Kelvin, hydrogen is moving at like 40 kilometers a second. So really, really fast. And as you cool hydrogen down, it moves slower and slower and slower. The heavier the molecule is, the more slowly it moves at a given temperature. And so the heavier the molecules go down on this plot. So what this means is that if you look at something like the Earth, okay, the helium and the hydrogen at the temperature of the Earth are all moving faster than the escape speed, and so they just escape off the Earth. Whereas the oxygen on Earth is moving more slowly than the escape speed, so it doesn't escape and it hangs around. And that's why our atmosphere has oxygen in it and not hydrogen. Okay? So if you look at the terrestrial planets, right, you can sort of see the Earth is not going to have hydrogen helium, Venus isn't going to have hydrogen helium, none of these things are. None of them are going to have hydrogen helium atmospheres. However, if you look up here at Jupiter and Saturn, the hydrogen helium hangs around, and that's why they have hydrogen helium atmospheres. Are there questions about that? Okay. Now, all these terrestrial planets, we think, started off with basically the same atmospheres. But they didn't end up with the same atmospheres. But we think in the very early solar system, all these rocks were basically the same mass, so they have kind of the same escape speeds. They're living in the same environment, and we think they all started with mostly the same atmospheres. They had outgassing from volcanoes, and they had cometary impacts, etc. So we think that they had carbon dioxide, a little water vapor, and nitrogen. So we believe that all those interterrestrial planets all started off with carbon dioxide, nitrogen, and water vapor atmospheres, and that's it. Okay? No hydrogen helium atmospheres, because that stuff wouldn't have stayed around. It would have been lost. Now, they evolved differently, though. So for example, they have greenhouse effects. Okay, so you have solar heating and atmospheric cooling. They balance. And it basically what this does is it helps determine whether or not you could have liquid water. If this water becomes liquid and starts raining out of the atmosphere, it can start draining carbon dioxide out, and that affects the greenhouse effect. Okay. The other thing that matters a lot for these planetary atmospheres is the magnetic field. So I've talked a little bit about this before, but our own magnetic field, right? The magnetic field of the Earth is protecting us from charged particles that are streaming at the Earth from the solar wind. They're coming at us from the sun. In the absence of that magnetic field, these charged particles would slam into the atmosphere of the Earth and blow the atmosphere off, basically. We think that's probably what happened on Mars. Whereas the Earth has a strong enough magnetic field now that it has not had this effect, and we've hung on to a lot of our atmosphere. So this is just a picture of this. I've shown something like this before, but you've got the solar wind coming from the sun, and here's the Earth with the strong magnetic fields coming out of it, okay? And that deflects charged particles. Why does the Earth have a strong magnetic field? Does anyone remember? Why does the Earth have a magnetic field? Say it.
Molten core.
Good. It's got a liquid core.
Spinning.
Sorry?
It's spinning.
It's spinning around. Great. So it's got this sort of molten core. You have these charged particles moving around. When you have charged particles moving around, that creates magnetic fields. Okay? So because we have a molten hot core, we've got this magnetic field. Thank you very much. We can be protected from the solar wind. Okay? Now, I'm going to skip this part. So, we've stayed hot. The inner part of the Earth has managed to stay hot. Why is that? Well, one of the basic reasons is that we're a pretty massive planet. And it turns out the time it takes for something to cool off depends on how massive you are. All right? So for example, you can actually derive this. I'll step you through it, although it's not, I'm not going to ask you about this kind of detail on the test. But you start out with some kind of heat or some kind of total internal energy of your hot bodies. Again, this is the beginning of the solar system. This is some constant times the radius of your planet cubed times its temperature. The radius of your planet cubed, that's just the volume. And the temperature of the planet gives you some sense of just what the average amount of kinetic energy that the things that make up the planet have, okay? So it's just the volume times the temperature. Now, anything that is cooling off, you have to spit, when you cool off, you are emitting energy out of your surface, okay? So if you have a sphere, the way that sphere releases, if you have a hot sphere, the way that sphere releases energy is it releases heat from its surface, okay? In just the same way that the sun shines, right, by spitting light out of its surface, anything that has a temperature emits emits electromagnetic radiation out of its surface. We are emitting energy out of our surfaces. It's infrared radiation, okay? That's the heat that's leaving our bodies, right? That's why we wear clothes when it's cold outside, because we trap that heat in, sort of like a greenhouse effect, right? So, and it turns out the energy loss rate goes like the surface area of the thing times it turns out the temperature you've got to the 4th power. So the surface area of your thing is what tells you the rate of heat loss, the rate at which heat can leak out of it. So you lose heat out of your surface area, but the total amount of heat energy that you have is related to your volume. This is important. This is why massive things tend to retain heat better than less massive things, okay? So animals that live in the Arctic tend to be kind of big animals, right? Polar bears are big, and that makes sense because they live where it's cold, but they're so big that they can actually contain a lot of their heat without leaking as much out of their surfaces. Your volume goes like your size cubed, but your surface area goes like your size squared. So the bigger your size is, the more volume you have per surface area. This is why big people tend to be warmer than small people. Okay, small people tend to get cold faster than big people too. Okay, it's the same thing. The more surface area you have, the more relative to your volume, okay, the more you're leaking, you know, the more energy you're leaking out per unit volume. Okay. Now finally, if you take a ratio of the cooling time, that is, if you figure out the cooling time, take a ratio of the total energy to the energy loss rate, that's roughly how long it ought to take you to lose all your heat. Okay? Remember, total energy goes like volume, the energy loss rate goes like surface area. Okay? And if you work this out, this is what it looks like. It's just the radius of your planet divided by the temperature cubed. So the bigger your planet is, okay, the longer it will take for you to cool off. And you roughly scale like your radius. So bigger planets cool off more slowly than little planets. Why am I talking about cooling off? Well, the hotter your core is, the more likely you are to be molten, and the more likely you are to have a magnetic field. Your magnetic field protects you from the solar wind and allows you to have an atmosphere. Atmospheres are important for life. Okay? So, if you look at the moon is a small thing. We think the moon probably doesn't have a molten core. If it does, it's very small, and it doesn't have much of a magnetic field. Okay? Mars has a pretty small molten core, if it has any molten core at all. So the large terrestrial planets like Venus and the Earth tend to have these magnetic fields because they haven't cooled off. Okay, they have these sort of hot interiors, and so it's the collective motions of stuff in these hot mantles that create these magnetic fields and allow us to preserve our atmospheres. Venus has a very big atmosphere, and the Earth has a nice atmosphere. And so we think that the existence of these magnetic fields and these bigger terrestrial planets is what allowed this to happen. Okay. Now, why do we care about, and so look at Mars. Sorry, let me just back up. Mars, on the other hand, basically has no atmosphere because it doesn't have much of a magnetic field and it's lost its atmosphere by the solar wind. Okay, so why do these atmospheres matter? I've talked about this before, but let's talk about it one more time, right? The greenhouse effect from the atmosphere can change your equilibrium temperature a lot. Just like putting on a big, thick winter coat, okay, can change the temperature you would have otherwise, right? It's the difference between being outside without a coat and being outside with a coat, okay? The surface of your body, which is like the surface of your planet, is warmer if you've got a coat on if you don't have a coat on. Now, your coat is still radiating energy from the outer parts of the coat, but it's also radiating energy back into your body and keeping you warmer, okay? And that's sort of what an atmosphere does for a planet. So, without an atmosphere, the Earth's temperature would be about 255 Kelvin. But with its atmosphere, it has a temperature of 287 Kelvin, which means water can be liquid. Venus, without an atmosphere, would be a little bit warmer than the Earth, but not that much warmer, right? Really not that much different than the Earth. But it's got a crazy, crazy thick atmosphere. It's got a crazy greenhouse effect going on. Its temperature is like 750 Kelvin. And so water is therefore vapor on Venus if it's there at all. Mars, on the other hand, has almost no atmosphere. So it has an equilibrium temperature of 214 Kelvin without an atmosphere, and with its measly atmosphere, it's about the same. It's too cold and the pressure is too low. In principle, you could have ice on Mars, but you're not going to have, certainly not going to have liquid water on Mars. Now, this greenhouse effect, however, can be very unstable, okay? what can happen is you can have something called the runaway greenhouse effect happen. Okay? So imagine you've got a planet that's sort of like the Earth, and the temperature goes up. Say the sun has a little bit of a period where it gets a little bit more intense. The Earth starts to heat up a little bit. You have higher air temperature that increases evaporation, and the warmer air holds more water vapor. Okay? If you get more water vapor, you get a stronger greenhouse effect, for example, and a higher air temperature. So over a short period of time, if you turn your atmosphere into steam, it can really heat up your planet. Okay? If this happens very, very rapidly, okay, this can create a runaway greenhouse effect where you basically steam up the planet and the water vapor itself starts heating it up. Okay? And eventually, if you also have, if this is going on while carbon dioxide is leaking up into the atmosphere, you can build up carbon dioxide in the atmosphere. You now no longer can rain because all the water is just steam. You can't wash that carbon dioxide back out of the atmosphere, and then you start having a huge amount of carbon dioxide, which is another greenhouse gas, and you just start to get this runaway effect. We think this is exactly what happened on Venus, by the way. Okay. So Mercury is another example of something that we think had a runaway greenhouse effect. We think Mercury started off with an atmosphere just like ours, but there was no liquid water on Mercury because it was just too close to the sun, too hot. So there was no way to shut down the carbon dioxide greenhouse effect, and basically what happened is the atmosphere just heated itself up by the greenhouse effect. It got so hot that it even lost its carbon dioxide, et cetera, and just boiled itself away. So we think Mercury is basically just too close to the sun, didn't have any liquid water to control its carbon dioxide greenhouse effect, and eventually just kind of boiled itself away. And now it's more or less a rock. Venus is another place where it just got too hot on Venus to hold on to liquid water, and you had this runaway greenhouse effect happening on Venus. Its average temperature is like 500 degrees Celsius, so it's crazy hot. So again, you know, while Venus probably started off looking a lot like the early Earth, something threw it out of balance early on that led to this runaway greenhouse effect, and now it just has this crazy carbon dioxide thick atmosphere because it probably had a period of early volcanism. None of that carbon dioxide was ever rained out because it just got too hot for liquid water, and it just built up and built up and built up, and it has this really thick, crazy hot blanket. So we don't think you're going to see a lot of life on Venus. It's just too hot. There's just no liquid water. Okay. Interestingly, when people used to look at Venus, Venus was like the favorite place to think about for life. Venus is sort of a sister planet, right? It's the same mass as the Earth. You could take images of Venus and it looked like it had cloud cover, okay? And people had these ideas that maybe there were lush rainforests on Venus, and that there were dinosaurs on Venus. There were all these stories about what might exist on Venus. And when we finally took our first probes and started to really study Venus in detail, it was pretty quickly apparent that it was too hot. There were no rainforests on Venus. Like, Venus is very different than people had sort of been hoping it would be. So Earth is sort of this Goldilocks planet. Okay, if you especially just look at it in the scheme of things, it's been this sort of amazing Goldilocks planet that was warm enough for liquid water. It had atmospheric pressure that was enough for liquid water. And the water was at the right level where it could rain out to sort of have you could rain out carbon dioxide and sort of stabilize a long-term carbon dioxide greenhouse effect to sort of keep the climate of the Earth pretty steady over time. We think that the early Earth probably had a lot more carbon dioxide in its atmosphere than the Earth does today. And that was actually important because the sun was not spinning out quite as much energy per unit time early on. The sun has actually changed over the last billions of years, and now it's a little bit brighter. So in the past, billions of years ago, the sun was fainter. It was spitting out less energy per unit time, but our atmosphere had more carbon dioxide in it, And so even in that past period of time, we had liquid water. And so over the long-term cycle of the sun getting cooler, we've actually had an effect where the long-term carbon dioxide cycle in the atmosphere has allowed us to sort of adjust to that and maintain conditions for liquid water. So it's sort of an amazing thing that it's stabilized over those long periods to allow liquid water for so long. And again, we have this amazing atmosphere today that's mostly nitrogen and oxygen. The oxygen comes from photosynthesis, which exists primarily, again, because we have this ample supply of liquid water and carbon dioxide so that photosynthetic plants and algae could evolve within this condition. Yeah, I've talked about Mars already, so I'm going to skip it. So the amazing thing is that if you look at the present-day terrestrial planet atmospheres, they're vastly different outcomes from basically very, very similar starting points. So the Earth's carbon dioxide content is only 0.035%, whereas Mars and Venus are basically all carbon dioxide. We have this hugely rich oxygen content, whereas Venus and Mars have basically no oxygen. And so the lack of oxygen and fundamentally these grossly, imbalanced temperatures on Venus and Mars make these things, we would sort of characterize these as uninhabitable planets, whereas we have this nice habitable planet, even though we basically started out very similar. Okay. The Jovian planets are farther out. And because they're farther out, they're colder, and so they could collect atmospheres that were now mostly hydrogen and helium, and we think they started off mostly hydrogen and helium. They are mostly gases and a little bit of ice. Neptune is sort of Uranus and Neptune are both about the same size, 15 to 20 times the mass of the Earth, whereas Jupiter is like 300 times the mass of the Earth, so it's the big thing. We think that they have teeny tiny little cores in the centers of them, but they're mostly gaseous out here, but they have incredibly high atmospheric pressures on those cores. I'll skip this. These are just nice pictures of Uranus and Neptune. These things are more icy and less gaseous, again, because they're farther away. The dwarf planets are these things here shown in comparison to the moon, and again, they're smaller little things. They have a lot of them actually do have little atmospheres, but they're pretty weak. And there's a bunch of other candidates besides the ones here shown, but this just gives you a sense of the sort of great variety of sizes of things that are orbiting the sun. Now, let me very quickly talk again about dwarf planets and like the whole Pluto story, right? Because, when I was growing up, I learned that there were 9 planets and the last planet was Pluto. All the kids liked Pluto because it was called Pluto. We thought it had something to do with the Disney character. But the weird thing about Pluto, it's always been weird, and the weird thing about Pluto is, not only is it pretty far away, but it has this kind of cockeyed orbit, okay? All the other planets orbit along in this very nice thin plane. But Pluto has this kind of crazy orbit that it gets closer to the sun and farther away from the sun, and it's not in the same plane as all the other planets. So it's always been this kind of oddball. And astronomers began to discover more and more things that are kind of out there, roughly in the vicinity of Pluto, that also had these kind of more cockeyed orbits, these kind of weird orbits that were farther out. They were a lot like Pluto, and eventually something was discovered that was even more massive than Pluto. And so astronomers began to realize that, look, either Pluto is something different. It's actually the first object found in this kind of new family of things. Or we're going to have to memorize the names of like 35 planets. And so eventually it was decided that Pluto would be sort of recharacterized as a dwarf planet and no longer a planet. And when I give talks to school kids, I say, don't think of Pluto being kicked out of the planet family. You just think of Pluto as having now a whole group of new friends, and it's now sort of got buddies out there that it can hang out with. So it's not a sad thing; it's a happy thing for our friend Pluto. It's like the ugly duckling story or something like that. So here's where they live. You know, they generally live farther out. Ceres is sort of an oddball. It's sort of like a giant asteroid that's so massive it's round, and sort of it got characterized as a dwarf planet. I wouldn't be surprised if these naming conventions change again. So we'll sort of see how this stuff develops. You know, bottom line is there's a bunch of things orbiting around the sun. Some of them are big and some of them are small. And so, you know, where you draw the line and where you call things planets versus not planets, like, you know, it's sort of a matter of definition. Now, something we'll talk more about next time is probably even more interesting and something that we don't think a lot about when we think about the solar system are the moons. Okay, so our planet has a moon. We call it the moon, right? And it's this big thing. Okay, here it is. Okay, and it's weird because it's big. Okay, all these other big moons in the solar system are orbiting either Jupiter or Saturn. So Jupiter, Saturn, Jupiter, Jupiter, Jupiter. Oh, here's Neptune. But otherwise, you know, it's just us that has this gigantic moon. All the other big moons are orbiting big things. So that's weird, and it has something to do with the formation history of our moon. You know, our moon probably formed in this crazy collision event. Most moons don't form that way. The other thing, though, that's important about these moons is these moons, turns out, are very interesting places to think about hunting for life. And that's because a lot of them, okay, for example, Europa here, and maybe Ganymede, have liquid water oceans underneath their icy surfaces. And in fact, probably have more liquid water on them than we have on Earth. The water is kept liquid not from energy from the sun, but from tidal energy from their host planets. The planets are squeezing them by tidal forces, and I'll talk about this some next time, and it's keeping that water liquid. And so you have these vast reservoirs, these oceans, on these moons that probably are also rich in organic molecules, and they have energy sources. And so people are very excited about the possibility that these moons actually are potential homes for life, maybe microbial life, and if that were ever discovered, it would be a huge, huge thing. It would be a really important thing, and it opens up a vast array of possibilities for life beyond the Earth. This is kind of cool. This is a picture of the moon Io, okay, right here, and this is Jupiter. So this is actually a real picture, okay, from the New Horizons spacecraft taken in 2007 of this little moon Io, okay, in front of Jupiter. The sun is up here shining light on both of them at the same time. Sort of amazing, like these are beautiful, beautiful images of these things that we've taken with spacecraft. I just put this here because it looks cool. You know, wow, you know. Okay. Let me take a second to talk about this other thing, Titan, down here. All right. So Titan is a very interesting moon. Here, it's got a dense atmosphere. So it can retain an atmosphere. It's cold enough that it can retain an atmosphere with methane and all kinds of stuff in it. And that methane is going to be very important, because it turns out that methane at these temperatures acts very differently than methane on the Earth. So let me skip this. Now, if you start thinking about the different kind of atmospheres that planets can have, we think that if your atmosphere is way too big, that's bad for life, because the atmospheric pressure will be so big it will just smash things, and we don't want that. So that's probably not good for life. So we think that the atmospheres in these Jovian planets are probably too thick and too crushing. Some of these other planets, like Mars, for example, probably have too small atmospheres. They're such low mass, okay, that they cannot hold on to much of an atmosphere, so they don't have much of an atmosphere, and that's also bad for life, because you remember you have to have a thick atmosphere in order to have any kind of atmospheric pressure to have liquid water, for example, or any kind of liquid, really. You need some pressure for that. Titan is a different example, right? Now, if you recall, on Earth, we're following the water, because on Earth it looks like all you really need to have life is liquid water. And so, broadly speaking, the first thing we ask when we look at some environment in the solar system or beyond is, could this thing have liquid water? Because it has liquid water, at least on Earth, when you have liquid water, you have life. So we're constantly thinking of liquid water as sort of a beacon for life, right? But maybe, okay, any kind of liquid solvent will do. So life on Earth relies on having this liquid solvent for these interesting chemical reactions to happen, to be sustained within. But there's this possibility that people have thought about is maybe it doesn't have to be water. Maybe any kind of liquid could host some kind of life form. Okay. So for example, water is a great liquid solvent because it's liquid from 0 degrees to 100 degrees Celsius. But you know, there's other things like ammonia can be liquid too if it's cold enough. Methane, if it's very cold, has a kind of narrow range of temperatures where it's also liquid. And ethane is maybe even better because it has a 100-degree temperature range where it can be liquid. So on Earth, you can have liquid water over 100 degrees range. And maybe you can imagine some foreign planet that it was cold enough that you had ethane acting as water on that planet that could also be some kind of liquid carrier for life. Okay. So here's liquid water. This was liquid methane or ethane. So this is this little object, Titan, that I talked about. So where should we look for life elsewhere in the solar system? Mars, maybe. We think maybe in the past it had liquid water, so it'd be very interesting to look at Mars as a past place for life, and we'll talk a bit about that. Titan, okay, has lakes of methane and ethane. We have landed probes on Titan. You can look at pictures of it. It rains methane and ethane on Titan, just like it rains water here. And it has little pools, and you have channels. And so there's a water, you know, just like there's a water cycle on Earth, there's sort of a methane cycle on Titan. And you could imagine, you know, if you wanted to think broadly, maybe there's some life form that has evolved utilizing that kind of liquid ethane as its water, as its sort of liquid. There are some wild cards, which I think are actually really promising things, like Europa and Enceladus, because these things, under their icy surfaces, have vast liquid oceans under their icy crusts. And again, this is something that we want to look at, potential place for life in the solar system. Okay, we'll talk more about that next time. Thank you.